Is it now shared? Okay, fine. Yeah, very good morning to all. Again, we'll come back to the session 4. That is, in the last class, what we have. That is, in the last class, what we have been seeing is that process management. Under process management, we have been seeing about process. Yesterday, what we have been seeing is that what is a process, what is the various kinds of responsibilities of operating system in connection with process management, and followed by the process concept is discussed in 3 dimensions. Number 1, process. Number 2, process state and process control block. And followed by, we have been seeing that process scheduling, and process scheduling is also covered in 3 dimensions. What are the different kinds of queues are there in your computer system, and what are the different schedulers are there for allocating jobs for this CPU, and finally context switch. Okay, what is context switch? A context switch is a small program which is responsible for saving and restoring the status of a particular process. Okay, a swapping is a small program, okay, which is responsible for temporarily swap out a program which is not currently required in memory and bring back the required programs into main memory. So this is what we have been seeing in the last class. Now we'll move into the today's topic is that operations on a process. Okay, so generally the operations of a process is classified into 2 categories. Number 1, process creation, and number 2, process termination. What do you mean by process creation? Process creation is a step. A process creation is a step which can be used for allocating resources to a particular process. Termination in the sense, once a process execution is successfully completed, what are the set of resources which has been already allocated simply written back to operating system. This is deallocation of resources is going to be called as process termination. So already in the last class, we have been seeing a definition called it as a process can be thought of as it is a program in execution. In order to execute such kind of a process, it required a resource like CPU cycles, memory cycles, IO devices, etc. But all these particular resources, all these particular resources has been under the control of operating system. So before executing any process, first of all, you have to make a requisition to the operating system. I want this. Some disturbance is coming. Okay, now once the process execution has been successfully completed, again you have to return back all the resources to operating system. That implies allocation of the resources to a particular process is nothing but process creation, and deallocation of resources to a particular process. Once the process execution is completed, it is going to be called as process termination. Okay, now once already we have been told one definition. One program is always runs in the system kernel, which is known as an operating system. Every time one program is always runs in main memory, which is going to be called as operating system. So operating system is the boss for your entire computer system. So whatever the jobs you are trying to execute, these all jobs are a child process for the operating system. That is, a master process is an operating system. My master processor are going to be creating child processes. And once the child process has been created, whatever the resources which is going to be required to execute the child process, that all resources must be allocated from the parent process. Suppose let us take an example. This is process ID number 1. It has been generated. Okay, another process, something like this, login, and it generated another process, call it as process ID 2, and it generates another process like this. Each and every process may generate any number of sub processes. That's it. This is going to be called as process creation. Now, when a process creates a new process, 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 there is two possibilities exist in terms of their execution. Okay? When a process creates a new process, two possibilities are exist in terms of their execution. Number one, parent continues to execute concurrently with the children. Parent and children both are allowed simultaneously to execute such kind of a process. Number two, the parent waits until okay, all the child process has been terminated. Parents has been okay, wait until all the child process has been terminated. Okay, that is now. So coming to whenever a parent process has been created, a child process, each and every already from the last class discussion, each and every process is going to be identified by using process ID number. Okay, which is uniquely assigned by an operating system to identify each and every process which is running on your computer system. So once a parent process has been created, a child process. Once a parent process has been created, a child process, whatever the resources which is going to be required for the child process, it is the responsibility of the parent process to assign all the resources to execute such kind of process. If the parent process is not having such kind of resources, it is the duty of the operating system, that is parent, super parent will going to allocate all the resources. That is, the resource sharing options are parent and child share all common resources. Child can share a subset of parent resources. Or you may have also third option, parent and child share no resources at all. And there is centrism. So that implies, and finally, the child will going to be getting resources either from the parent process, in case, or otherwise, you are going to be getting resources from the master parent, that is from operating system. And coming to the next very important one is that executing options. Whenever a parent process has been created, a child process. Whenever a parent process has been created, a child process, in terms of their execution, there are two possibilities are there. Parent and child can concurrently execute. Parent and child both are allowed simultaneously execute. Or second option is that then parent will going to be waits until all the child process has to be terminated. These are the only two options. Now, once a process creation has been successfully done, whatever the resources which has been allocated, that is also done. Once the process execution is also done, then what you need is that next very important step is that process termination. What do you mean by process termination? Simply says the deallocation of resources. Simply nothing but deallocation of resources. That implies whatever the resources which has been already allocated to that particular process, it is the responsibility to return back all the resources to operating system to execute for some another processes. Now coming to the next question. So once how it is going to be done? It is going to be done by using an exit system call. Let us take an example before in Unix operating system. Whenever a parent process want to create any child process, you have to use a command, call it as a small function fork. A fork is a system call which can be used to create a child process. So once a child process has been created, if you want to execute it, ECVE command function can be used to execute such kind of a process. Once the process execution has been successfully completed, an exit is a command which can be used to terminate the execution of that particular process. That's why whenever while executing a process, the last statement of the process is always exit. That implies whatever the set resources which has been already allocated to you, please try to return back all these particular resources. That is returns. That is, it returns the status data. It returns status data from the child to parent via a wait system call. You know already what is a system call. It is acting as an interface between a process and the operating system. Again, the parent may now correspondingly there is the parent may terminate the execution of a child processes using a command call it as abort. Okay, so parent may terminate. The parent is always having a right to do any kind of operations on a child. The parent may terminate the execution of a children processes using an abort system call. Okay, what is the various reasons? Parent, why forcibly stopping the execution of a particular process? That implies the child has exceeded the allocated resources to that particular process. Okay, whatever the set of resources which has been allocated to that particular process, if the child is exceeded, Okay, the child is uses more number of resources. That's why in this particular situation, the parent process may forcibly stopping the execution of a child process. And the second very important thing is that whatever the task which is assigned to the child process, which is no longer needed by the parent process, whatever the task which is assigned to the child process, which is no longer needed by the parent process, at the moment also the parent will forcibly stopping the execution of the process. Now, the third very important option is that the parent is adjusting and the operating system does not allow a child to continue if it is a parent terminates. If once a parent is terminated, the child is also forcibly terminated. That's it. Now, that is, these are the three options. Suppose if let us take whenever a parent want to terminate, first of all, the parent has to see that all the child processes has to be terminated. Then only the parent is allowed to terminate the process. Now, suppose if the parent want to terminate, then forcibly all the child has to be terminated. This kind of a termination is called it as cascading termination. Whenever a parent is terminated, then your operating system not allowing you to continue all the child processes. It forcibly stop the execution. That's it. Now we have a small keywords which can be useful for you for our GATE examinations. For GATE examination, Zombie. What do you mean by zombie? If a no parent is waiting, then it issues a system call it as zombie. Often, if a parent is terminated without invoking wait, if the parent is if a parent is terminated without invoking a wait, then it is going to be called as orphan. Okay, this is going to be called as process creation and process termination. Simply, you can say that creation of a process is nothing but allocation of resources. Process termination is nothing but the allocation of resources. And coming to the next very important topic of this session is that cooperating process. Now already we have been seen in the previous class multi-programming. So what is multi-programming? In the sense more than one program can be simultaneously reside in main memory during the execution of one particular program. Okay, in case if any program requires an IO operation, the CPU does not sit idle. It simply Maliki. Executing one particular process, in case if any process needs a communication, in case if any process requires an IO operation, the CPU does not sit idle. It simply switches from one particular job to another job. Like this, interleaved fashion of execution, giving a look and feel that all the jobs are happening simultaneously. Similarly, we are also seeing about multiprocessor organization. In a multiprocessor organization, more than one CPU can be simultaneously reside on the same machine. They are closer to communicate in order to establish the communication between the processes. If they're using same clock pulses, same buses, same memory, such kind of a technology is called it as parallel system technology. And in order to establish the communication between the processors, if they're using separate clock pulses, separate buses, and separate memory, then it is going to be called as a distributed system technology. Now, either a uniprocessor organization or it may be a multiprocessor organization, simultaneously there are more than one. We call it as concurrent process execution. The concurrent process execution is going to be classified into two categories. Number one, independent process organization. Number two, cooperative process organization. Concurrent process execution is mainly classified into two categories. Number one is independent process organization. Number two is going to be called as cooperative process organization. Whenever two processes are said to be independent, provided while one is executing, it does not affect or affected by any other processes, then such kind of a thing is called as independent process organization. Okay, whenever two processes are said to be independent, provided if one is executing, it does not affect or affected by any other processes, then it is going to be called as independent process organization. Whereas in the case of second one, cooperative. Whenever two processes are said to be cooperative, whenever two processes are said to be cooperative, while one is executing, it can affect or affected by other process. And such kind of a thing is going to be called as cooperative process organization. And such kind of a process is going to be called as cooperative process organization. Now, So that implies, what is the meaning of this? Means the meaning of this, whenever two processes are said to be cooperative, provided they are having a common resources. Okay, there is some resources are shared between that particular processes. But there is in the case of an independent, they are not sharing any kind of resources. They are not sharing any kind of resources. So the concurrent process execution has been classified into two categories. Number one, independent. Number two, cooperative. A process is independent if it cannot affect or affected by any other process executing in the system. That implies clearly, it says that it does not share any data. It may be a permanent data or it may be a persistent data, whatever it may be. There is no data shared between the two processes. That implies there is no data sharing. That implies if one is executing, it does not affect or affected by other processes. But whereas in the case of whenever two processes are sharing the any particular data, while one is executing, if this process makes any modifications, the modifications is affected by that process. Then such kind of a thing, which is going to be called as cooperative process organization. So finally, I conclude that cooperative process in the sense whenever two processes are said to be cooperative, while one is executing, it can affect or affected by other processes. That's it. What is the reasons for providing cooperative process organization? There are several reasons for providing an environment that allows a process cooperation. Number one, information. If the same task is distributed for several processes at the same time, so that we can run faster. That is, if you want a particular task to be run faster, we must break them into subtasks, and each of which will be executed in parallel with the other. Okay. Now, the very important point is that the speed up can be achieved only if the computer has multiple processing elements. Otherwise, it is not possible. It should multi-processor organization. Otherwise, in case if you're having only one CPU and one IO processor, maximum you can do only two jobs at a time. One is for executing, another one is for IO operation. So that you should have a more number of computing elements. That is CPUs and IO processors, or may call it as IO channels, should be there on your computer system. Otherwise, the computation speed up will not going to be done. Number three, modularity. So everyone knows that a problem is not going to be solved as a whole. And the problem has to be divided into a number of subproblems, solve each and every subproblem, glue together all these particular pieces in order to solve the whole problem. That is modularity concept. Then now why you're dividing the problem into a number of small pieces? For your convenience, for handling it very efficient manner. Now, how can you understand this cooperative process organization? It can be explained by using a small concept known as producer-consumer problem. Okay, this is also we are going to call it as buffer management. What is this one? First of all, let us well define what is a buffer. A buffer is simply defined as it is a part of main memory where you're it is a part of main memory. A buffer is a part of main memory where your all IO operations are routed through only buffer. All IO operations are routed through buffer only. So let us take a small example. Okay, suppose if you want to print any part like this. So the printer is consuming one item from the buffer. Okay, printer is consuming one item from the buffer, and your CPU is going to be producing one item into the buffer. Okay, that's why this problem printer is going to be called it as a consumer, and your CPU is called it as a producer, hence it is going to be called it as producer-consumer problem. That is, consumer consuming the items from the buffer and producer producing an items into the buffer. Now, in case if there is any speed mismatch between producer and consumer, in some situation, producer must be wait until consumer consuming an item from the buffer. Similarly, if the consumer want to retrieve any particular item, okay, first of all, consumer must be wait until producer producing an item into the buffer. That's it. So in case the speed mismatch is just in some situation, producer may wait until consumer consuming an item from the buffer. In some situation, consumer may wait until producer producing an item into the buffer. And that's it. This is how. This is this is implemented by using circular queue. Already you're in circular queue. We have a small problem is going to be called it as okay, while writing a programs in data structures, in circular queue is having a small disadvantage. We cannot say that when the queue is full and when the queue is empty. So we are getting the same condition for queue full and as well as queue empty. In order to overcome this particular problem, we need to do two things. Number one, either we need to leave one memory location empty, or otherwise you need to use an additional variable n, which can be used to count how many number of elements that is presented on the queue. Suppose if the buffer size is 50, I will take count. If count is equal to 50, buffer is full. If count is equal to 0, buffer is empty. That's enough. So depending upon the counter value, producer is allowed to, if the counter value is less than 50, then producer is allowed to place the items onto the buffer. If counter value is greater than 0, then consumer is allowed to retrieve the items from the buffer. If counter is equal to 50, producer is not allowed to place any items onto the buffer. If the counter is equal to 0, consumer is not allowed to retrieve any item from the buffer. That's it. This is it. That implies both producer and consumer in one sharing a common memory location, that is buffer. Point number one. Number two, producer and consumer both are sharing counter variable. Suppose let us take an example. If counter is equal to 5, that is there are 5 items in the buffer. There are 5 items in the producer produces an item. Then after producing an item, counter value becomes count plus 1, that is 6. Suppose if the consumer is consumed 1 item, again 6 minus 1, it becomes 5. That implies producer and consumer both are operating on count variable. Producer and consumer both are operating on count variable. Producer is making count is equal count plus 1, consumer is making count plus 1. That implies producer and consumer both are sharing a common variable count. Hence this particular producer consumer problem is named as cooperative process organization. This bounded buffer problem can be dealt by using, okay, we have in your standard textbooks, it is dealt in 2 ways: unbounded buffer problem and bounded buffer problem. Unbounded in the sense there is no practical limit on the size of the buffer. There is no practical limit on the size of the buffer. So that's why there is no problem at all. So producer can produce items, consumer can consume items from the buffer, there is no problem. But if the problem comes with only bounded buffer problem. Okay, now we'll see how the solution is implemented for this. Now I'm defining, okay, define buffer size is equal to 10. This is hash defined in the sense I am defining a variable, call it as buffer size, which is a constant. The value is 10. So wherever you have buffer size variable is there in the program, please try to substitute the value of 10. It is nothing but a macro. You know what is a macro? A macro is an instruction to the a macro is in, it is pointing to 0. That implies okay, which is used to produce an items. In is a variable which can be used to allow the items into the buffer. Whenever an item is allowed, in is automatically incremented, and out is a variable used by consumer. Whenever an item has been removed, out is automatically moved. Initially, in is equal to 0, out is equal to 0. Both are pointing at starting position. If the solution is correct, but if it can only use buffer size minus 1. Already I told that the data structure which is used for implementing bounded buffer problem is circular queue. So already I told that in a circular queue, we are having a small problem, call it as when the queue is full and when the queue is empty. We cannot say. Why? Because while writing a program, we are getting the same condition for queue full and as well as queue empty. In order to distinguish that when the queue is full and when the queue is empty, you need to leave one memory location empty, or otherwise you need to use an additional variable which can be used to count how many number of elements that is present in the queue. So this is a very important one. Okay. So buffer, in case I haven't defined it as 10, but you can eligible for using only 9 items. Okay, more than 9 you cannot use it. Otherwise you can get a problem when the queue is full and when the queue is empty. It is this. Now we'll see the producer problem. Now we're going to see the code for the producer problem. So whenever a producer want to produce any item onto the buffer, so that is first of all you want to produce one item, next to produce. While true, this process is repeated until the whole program execution has been successfully completed. So producer produce an item. Then producer has to be checked that in plus 1 divided by buffer size. That is, in case if any number is divided by 9, the remainder is 0 to 9. Yes. Okay. So it is equal to 9. That implies divided by 9 is equal to out. That implies in and out are both are residing in same position. That implies the buffer is already full. You are not eligible for placing any items on the buffer. That's send it. I have been put in a semicolon here. That implies the loop is not valid for any statement. By default, any control structure is valid for only one statement. If you put a semicolon for any particular loop, that implies, okay, the loop itself is going to be executed. That is not valid for any one of the statement. It is valid for itself. So, in case in plus 1 mod size is equal to out, that implies the buffer is already full. You are not allowed to place any items onto the buffer. If in case if the buffer is not full, then you can allow to produce your item into n, and after that n is equal to n plus 1. Okay, why we use modular symbol is that 0, 1 to 9. After 9, again we need to come back to 0. It is in a circular queue manner. That's why this is producer process. And consumer process. Okay, in consumer, okay, want to consume one item. If in is equal to out, that implies there is no items in the buffer. There is no items in the buffer. That implies you are not eligible for retrieving any item from the buffer. Again, I put a semicolon here. That implies, okay, buffer is empty, you do nothing. Suppose in case if in is not equal to out, that implies there is some items in the buffer. Now you read that item and place it, and out is equal to out plus 1 mod size. That implies again like this. This is producer and consumer. Okay, and one additional thing is that here we have written a code by using size -1. That's why I'm not using any additional variable later. In the next one, we'll see how in process synchronization, we'll see how count variable is going to be affected. So this ends our discussion about process. Now we'll move on to process scheduling. That is the next topic of discussion. That is the next topic of discussion in process management is that CPU scheduling. The next topic of discussion is CPU scheduling. Now, process management and CPU scheduling. So you know that CPU scheduler, process scheduler, or short-term scheduler, everything is same. Now, already, what is scheduling? Already you know that CPU scheduling is basis for multi-programming operating system. CPU scheduling is basis for multi-programming operating system. Already in the previous sessions, you already know that what is multi-programming. More than one program can be simultaneously reside in main memory. Once more than one job is there, how can the CPU can decide that which job is going to be executed first? Which job is going to be executed first? To see that, okay, there is always some processes running all the times by your CPU. That is the main duty of this one. Okay, that is your heart of your operating system. The operating system is invented mainly for the purpose of keeping the CPU busy at all the times. The operating system has been mainly created for the purpose of keeping the CPU busy at all the times. Who is responsible for keeping the CPU busy at all the times? Your CPU scheduler program is always responsible for supplying a program, okay, to the CPU and make the CPU busy all the time. Now, before going to the detailed discussion about some CPU scheduling algorithms and some problems on CPU scheduling algorithms, first of all, we'll see that CPU and I/O burst cycle. So I have been given so many definitions. Okay, already I have been given one definition for a process. A process is thought of as a program under execution. Another definition is that a process is a continuous collection of CPU and I/O burst cycles. A process is a continuous collection of CPU and I/O burst cycles. What is the meaning of this? Suppose let us take you have been written one program like this. In this first one you have been written load, store, add, store, something you written. These are all calculation statements. These all calculations is done by CPU. So already I told that every computer system is having minimum 2 processors. Number one is CPU and second one is I/O processor. Okay, CPU is responsible for executing input and output. Sorry, it is an I/O. You need to get the data from an I/O device. So all I/O operations are routed through I/O processor. So now this read from file is going to be done by I/O processor. And until that, okay, you need to wait for it. So meanwhile, the CPU does not sit idle, it switches to some other process and execute it. Followed by store, increment, index, something. And all calculators on like this. That's why I have been defined as a process is a continuous collection of CPU and I/O burst cycles. Okay, let us take an example. The time with CPU, then I/O processor. But whereas in the case of I/O bound process, a process said to be an I/O bound process if it is spending most of the time with I/O processor than CPU operations. That implies simply Suppose let us take another definition of CPU bound process is that if the number of CPU bursts is greater than number of IO bursts, then it is going to be called as CPU bound process. If the number of IO bursts is greater than number of CPU bursts, then it is going to be called as IO bound process. Now already I told that CPU scheduler, or you may call it a short-term scheduler, or you may call it as process scheduler. Okay, so what is this definition of CPU scheduler or short-term scheduler or process scheduler? It is responsible for selecting one job from ready queue and supplying the CPU and make the CPU busy at all the times. Now, coming to the next one, schedulings. So now, short-term scheduler. Short-term scheduler is CPU scheduler, short-term scheduler, process scheduler, all are same. So it is a responsibility of a CPU scheduler is selecting one job from ready queue and supplying to the CPU and make the CPU busy at all the times. Now, your scheduling algorithms are mainly classified into two categories. Your scheduling algorithms are mainly classified into two categories. Number one, preemptive scheduling. Number two is going to be called as non-preemptive scheduling algorithms. Number one is preemptive scheduling. Number two is going to be called as non-preemptive scheduling algorithms. Preemptive scheduling. What do you mean by preemptive? What do you mean by preemptive scheduling? So, preemptive scheduling in the sense forcibly stopping the execution of one particular process and giving the control of the CPU to some another process. Okay, what is this? Okay, forcibly stopping the execution of one particular process and giving the control of the CPU to some another process is going to be called as preemptive scheduling. Whereas in the case of non-preemptive, okay, the CPU releases its control from a particular process after that if the execution is successfully completed. Otherwise, the CPU will not going to be switched to one particular process to another process. The CPU control is leaved from one particular process to another process only when the process is successfully completed. Okay. So, under that is, under the non-preemptive scheduling, once the CPU has been allocated to a process, the process keeps the CPU until it releases the CPU either by terminating or by switching to the wait state. Otherwise, the CPU will not going to be given. So, forcibly stopping the execution and giving the control of the CPU to some another one is called it as preemptive. Okay, if it is not done like that, it is called it as non-preemptive. So, now we move on to, okay, say in which case we need to take preemptive decision and in which case we are going to be taking non-preemptive case. And the last class we have been seeing that process states. The process states has been classified into 5 categories: new state, ready state, running state, waiting state, and terminated. There are 5 states. Okay. Now among this particular one, the CPU scheduling decisions may be taken in place. So when I'm switching from running state to wait state while executing one particular process, whenever an IO operation is encountered, the process is shifting from running state to waiting state. While executing one particular process, that is while running one particular process, whenever an IO operation is encountered, according to multi-programming, the CPU does not sit idle. It simply put the job in waiting state and asking the IO processor to schedule that job, and CPU does the normal execution. We are not forcibly stopping the execution of any particular process. According to multi-programming, the CPU is going to be switching from one particular process to another process. Hence, in this situation, the scheduling decision is non-preemptive. In this particular situation is non-preemptive. Now, let us take another one. When the process is successfully completed. So once the process is successfully completed, the next job is process termination. That is, once a process termination is nothing but simply deallocation of resources. The resources is once deallocated, we are not forcibly to stop any one of execution. The process successfully terminated, then CPU automatically takes another job from the ready queue and execute it. In this particular situation is also the decision from the ready queue is only non-preemptive. So in this case 1 and case 4, both are non-preemptive case. Number 3. Now, when a process running state to ready state, when a process comes from running state to ready state, so whenever while executing a low priority process, a high priority interrupt has been encountered. What is that? The low priority process is preempted and the response is given to high priority. At that moment, we are forcibly stopping the execution of current running process and giving the control to high priority process. In this situation, we are forcibly stopping. Hence, it is preemptive scheduling. Hence, it is preemptive scheduling. Suppose now, case 3, waiting state to ready state. So, once IO operation is completed by the process selected by short-term scheduler. Short-term scheduler, or may call it a CPU scheduler, selecting one job from the ready queue. So whatever the job which has been selected, so immediately we need to allocate CPU to that particular process. Who is responsible for allocating the CPU to that particular process? That is done by dispatcher. So dispatcher is only allocating CPU, no other things. Yes, dispatcher is also doing some another thing. Switching context. What do you mean by switching context? So saving and restoring the status of a particular process. So already I told that before switching from one particular process to another process, okay, before switching from one particular process to another process, first of all, you need to save the status of the current process where it has been stopped somewhere in the stack. And again, you need to go to that particular process. Once the process execution is completed, again, you resume it. This is going to be done by context switch. That is, switching context is also going to be one of the part of dispatcher. Number 2, switching to user mode. In the switching to user mode, whenever a new process has been allowed, so the new process has to be given by user only. That's it. Now, coming to the next, third very important one is jumping to the proper location of the user program area to start execution. Already you know that everyone. So whenever the user is trying to execute any particular program, first of all, the program should be copied into main memory and give the starting address of the program to program counter for initiation of execution. The starting address should be also be done by this one guy. These all three things is done by dispatcher. The time it will going to be taken, the time it will going to be taken for the dispatcher to stop one process and start another process is called it as dispatch latency. The time it will going to be taken for stopping one particular process and start executing another process, this particular time, in between this particular time is going to be called as dispatcher latency. This is going to be called as dispatch latency. Now, coming to the next very important one is that, okay, before going to the detailed discussion about scheduling algorithms, now we're going to see scheduling criteria. So whatever the algorithms you are trying to design, whatever the algorithms so far which has been already invented in the market, okay, these algorithms has been designed with following goals on mind. The scheduling, this is going to be named as scheduling criteria. The scheduling criteria may depend on the following points. Scheduling criteria may depend on following points. What is this? Number 1, CPU utilization. Number 2, throughput. Number 3, turnaround time. Number 4, waiting time. Number 5, response time. So coming to the first very important one is CPU utilization. You have to design a scheduling algorithm in such a way that the CPU utilization must be always maximized. Okay, what is CPU utilization must be maximized? The main motto behind inventing operating system is that to keep the CPU busy at all the times. The operating system is invented for the purpose of efficient utilization of CPU. That's why the first goal of your scheduling algorithm is that CPU utilization must be maximized. Number 2, throughput. So let us define what is a throughput. A throughput is going to be simply stands for the number of jobs that is completed on a given unit of time. Throughput is simply defined as the number of jobs that is completed on a given unit of time. You have to design an algorithm in such a way that the more number of jobs are going to be completed in a short amount of time. That is going to be called as throughput. Throughput is simply defined as the number of jobs that is completed on a given unit of time. So you have to do more number of jobs in a small fraction of a second. Number 3, turnaround time. What is a turnaround time? Turnaround time is simply defined as the time gap between job submission and job completion. Or you can talk it as the time gap between entered into the ready queue and exit from the ready queue. This time gap is going to be called as turnaround time. That is the total amount of time that has been spent in the ready queue for executing that particular process is going to be called as turnaround time. Or you may simply define it as the interval from the time of submission to the time of completion is called turnaround time. Okay. Turnaround time. Now turnaround time must be minimized. Why minimized? You have to take only less amount of time. Your CPU is having a capability of executing millions of instructions for a small fraction of a second. So you don't spend most of the time for executing it. So that turnaround time must be minimized. Now, waiting time. What is waiting time? In order to execute your process, how much amount of time you have been waited in the ready queue is going to be called as waiting time, or you may define it as sum of all the time spent on the ready queue for executing your process is going to be called as waiting time. Sum of the period spent waiting in the ready queue, simply it is defined as sum of the period spent waiting in the ready queue. And this is also, waiting time is also minimized, turnaround time is minimized, and response time after entering into the ready queue, when the CPU has been given a first response, after entering into the ready queue, when the CPU has been given a first response is called as response time. It is going to be called as response time. That is, so turnaround time should be minimized, waiting time should be minimized, response time should be minimized, CPU should be utilization maximized, and throughput is maximized. So this will demonstrate by using a small example. Let us take an example. I need to start the class at 10:30 and I need to finish the class by 12:30. I haven't started the class at 10:30. I need to finish by 12:30. This is the time slot what has been assigned. Now, let us take. Suppose, actually what happens is, I assume that I am the CPU. There are already some jobs are there in the queue. There are already some jobs are there in the queue. Now I have been entered into the session at 10:10. I have been entered the session. Sorry, I have been entered the session at 10:40. My class is scheduled at 10:30 to 12:30, but I have been entered into the session at 10:40. I thought for 1 hour. Again, I took 10 minutes of break. Again, I thought for some amount of time. Again, I have been taken another 5 minutes of break and the session is end. This is what is this. Now, initially I have been late by 10 minutes and in between I have 2 slots, that is 10 minutes for making some another action and 5 minutes for talking with my phone. I have been spent it. Now, your turnaround time, you are already entered, the students are entered at 10:30 and the students are came out at 12:30. The turnaround time is 2 hours, that is common. Waiting time, in order to complete my class, the students has been how much amount of time they have been waited? Initially 10 minutes, in between there is 2 time gaps, that is one 10 minutes, another one is 5 minutes. Totally 25 minutes of time the students has been waited for me to complete the class. That is waiting time, the sum scheduling algorithms. So scheduling algorithms is already, again I'm defining, it is the responsibility of process scheduler selecting one job from ready queue and supplying the CPU and make the CPU busy at all the times. So what are the different kinds of scheduling algorithms which is available in the market? In the sense, these are the different kinds of scheduling algorithms which is available in the market. And coming to the first one, okay, first come first served scheduling. Number 2, shortest job first scheduling, or you may call it as shortest remaining time first scheduling. Shortest remaining time first scheduling. And the third very important one is that priority scheduling. Number 4, round robin scheduling. Number 5, multi-level queue scheduling. Number 6, multi-level feedback queue scheduling. These are the multi-level queue feedback scheduling. These are the different algorithms what we are going to see now along with the problems. Now coming to the first one, first come first served scheduling. Coming to the first one, first come first served scheduling. So simply the algorithm is simple, only one line of algorithm. Okay, what is this one line of algorithm? We'll see. Okay, which process is arrived first in the ready queue? That job is going to be scheduled by your CPU first. That's it. First come first serve. Which job is going to be arrived into the ready queue first? That first job is going to be scheduled first. That is going to be called as first come first serve scheduling. How can we explain? Okay, this can be explained by taking a small problem. Okay, I'll take in one problem. Okay, the given problem like this: process and burst time, and they ask you to calculate. There are three processes are running. There are three processes running: process P1, process P2, and process P3. In order to execute process P1, it requires 24 microseconds, 24 milliseconds. And in order to execute process P2, it requires 3 milliseconds. In order to execute process P3, it requires 3 milliseconds. And they ask you to calculate what is the average waiting time and average turnaround time. They ask you two questions: average turnaround time and average waiting time. Average turnaround time. Now, coming to the first one. The problem is they ask you to calculate average waiting time, average turnaround time. They ask you. So now there are three jobs are there in ready queue: process P1, P2, P3. In order to execute process P1, burst time in the sense how much amount of time that is required to complete the job. In order to execute process P1, it requires 24 milliseconds or microseconds, whatever it may be. In order to execute process P2, it requires 3 milliseconds, and in order to execute process P3, it requires 3 milliseconds. Suppose the processor arrived in the order same P1, P2, P3. The Gantt chart representation for the above process: first P1 is started. It takes how much amount of time? 24. 0 plus 24, it becomes 24. 24, and after that P2 is started. So P2 is now, I have been indicated here, P2. 24 plus 3, now it becomes 27. And 27 after that P3. So P3 is entered into the queue. That is 27 plus 3, 30. Now I'm calculating the waiting time for P1. P1 is waiting time is 0. P1 is not waited for anyone. It is whenever it has been entered into the queue, immediately it has been started. The waiting time for P2 is, it has been waited until P1 is completed. That implies P2 waiting time is 24. The waiting time for P3 is that P3 is waited until P1 and P2 has been completed. P3 is waited until P1, P3 has been completed. That is, P3 has been waited for how much amount of time? 27. How much amount of time? 27. That implies the total average waiting time is equal to 0 plus 24 plus 27 by 3. That is equal to 51 by 3. That is equal to 17. So the average waiting time of this processes is 17 milliseconds. Is it clear? Now, coming to the next one, turnaround time. Okay, so already I told that, okay, waiting time, sum of all the times which has been spent in the ready queue in order to complete a particular job. P1 is waited for only 0 seconds, P2 is waited for 24, P3 is waited to 6 plus 0 plus 3 by 3, only 3. Now in this particular case, you are getting 17. In this particular case, you are getting 17. If you take the shortest jobs first, so that the average waiting time is reduced. This is the idea behind for the next algorithm. Now, the average waiting time. There is a small dynamic situation. Already you know that in the earlier class, if CPU, if a long-term scheduler select all CPU bound processes or select all IO bound processes, what happens is that the CPU is going to be sitting the most of the time idle. In order to overcome such kind of an idleness, the long-term scheduler has been replaced with the short-term scheduler. Okay, long-term scheduler is replaced with short-term scheduler. Sorry, long-term scheduler replaced with medium-term scheduler. What is this particular medium-term scheduler? Medium-term scheduler is select a good process mix from secondary storage device to main memory. Okay, so that the CPU idleness is going to be reduced. Such kind of an effect is going to be called as Conway effect. Okay. So now this first come first served scheduling is anyone can tell me that whether it is preemptive scheduling or non-preemptive scheduling? It is purely non-preemptive scheduling. Why? Because P1 execution is never stopped until CPU burst. That job is going to be executed. Now in this particular shortest job for scheduling, there are two kinds of titles are there in your textbooks. Shortest job for scheduling, shortest job remaining first scheduling. So we have two cases. Case one, if all the jobs are arrived at the same time, then how we are going to be calculate average waiting time and average turnaround time. If okay, the jobs are arrived at different clock pulse period time, how do you calculate it? We'll see the both examples in a problematic way. Now coming to the first one, case one, non-preemptive case. So non-preemptive in the sense I'm saying that all the jobs are that is arrived at the same time. All the jobs are arrived at the same time. Now I have been taken a problem. Okay, process. There are 4 processes running in a computer system. The burst times are given, and they ask you to calculate what is the average waiting time and average turnaround time of this processes. Now the problem is there are 4 processes running. In order to execute process P1, it requires 6 milliseconds. In order to execute process P2, it requires 8 milliseconds. In order to execute process P3, it requires 7 milliseconds. In order to execute process P4, it requires 3 milliseconds. So the Gantt chart representation for this is that this one. Among all these processes, which process is going to be taking less amount of time? That is first one, P4. That's why I have been taken. First one is P4. It takes 3 milliseconds. So 0 plus 3, now it becomes 3. The next shortest one is 6. So I take P1, 3 plus 6, now it becomes 9. Now after that, the next shortest is P3. I'll take P3 here. So 9 plus 7, it becomes 16. And after that, okay, the last one is P2. 16 plus 8, it becomes 24. Now I'll calculate the waiting time for each and every process. The waiting time for P1. So P1 is waited until P4 is complete. That's why the waiting time for P1 is 3. The waiting time for P2 is 16. Why? Because it has been waited until P1, P4, P1 and P3 all are completed. The waiting time for P2 is 16. The waiting time for P3 is 9. It has been waited for P1, P4 both has to be completed. The waiting time for P4, but P4 is not waited for anyone. Once it has been entered into the queue, immediately it started, that's with 0. So that average waiting time is equal to P plus 16 plus 9 plus 4, 0 by 4, that is equal to 7. That is equal to 7. Now, turnaround time. Turnaround time is nothing but the time gap between job submission and job completion. So P1 is completed at 9. P2 is completed at 24, P3 is completed at 16, P4 is completed at 3. So sum altogether divided by 4 is going to be called as average waiting time 13. Now you can observe in this particular case, I am not forcibly stopping the execution of any one of the process until their execution is complete. Hence it is going to be called as non-preemptive. This kind of a case is going to be called as non-preemptive. We are not forcibly stopping the execution of any particular process. We are not forcibly stopping the execution of any particular process. Hence, it is going to be called as non-preemptive scheduling. It is going to be called as non-preemptive scheduling. Observe it. Is it clear, everyone? Now we'll go on. This is case 1, non-preemptive. The case 2, preemptive. So the all jobs are not arrived at the same time. That's why this is also named as shortest remaining time first scheduling. This is 8 milliseconds. Process P2 arrived at clock pulse 1 and it requires 4 milliseconds. Process P3 arrived at 2 and it requires 9 milliseconds. Process P4 arrived at third second, it requires 5 milliseconds. It requires 5 milliseconds. It requires 5 milliseconds. And they ask you to calculate what is the total turnaround time and waiting time. Amount of time it will going to be taken. Now it takes, it requires 7, it requires 3 and this is 9. Which one is shortest? Again P2. That's why again P2 is continued. After another second, again P4 is entered. After the third second, there are 4 jobs are there. In order to execute process P1, it requires 7, it requires only 2, this requires 9, this requires 5. So only the shortest one is P2. That's why P2 is continued. It's clear? Now, after that, no jobs are arrived. So the next shortest, after completion of P2, the next shortest one is 5. That is P4 is completed. And this is 7 and this is 9. So 10 plus 7, it is 17. And after that, P3, that is 17 plus 9, it becomes 26. So now we need to calculate the waiting times for each and every process. The waiting time of P1. Now the waiting time of P1 here is 0. It comes at 0. 0 minus 0 plus here waiting time is 10. Earlier it stopped at 1. That implies 10 minus 1, it is equal to 9. That's why I have been defined 10, but it arrived at 3, 10 minus 3 is 7. So average waiting time is equal to 17 plus 4 plus 24 plus 7 by 4, that is equal to 13 minutes. That's it. Now you can observe in this, P1 is forcibly stopped the execution and giving the control of the CPU to process P2. Why? Because it requires a less less burst time. That's why we are forcibly stopping the execution of process P1 and giving the control of the CPU to process P2. So we are forcibly stopping the execution and giving the control of the CPU to some another process. Hence, it is going to be called it as preemptive scheduling. So, shortest job first scheduling is either preemptive or non-preemptive. Shortest job first scheduling is preemptive or non-preemptive. Now, coming to the next one. So, now we have been finished about two. The first one is first come first served scheduling. It is purely non-preemptive. Shortest job for scheduling is either preemptive or non-preemptive. If the arrival times are not specified, it is non-preemptive case. If the arrival times are specified, it is preemptive case. Now coming